Thank you everyone for giving us an introduction. And next up we have Cory LaNou. He's going to give us a pprof presentation for about half an hour, and then we'll have Q&A right after. So with that, Cory, take it away.
All right, fantastic. So I always like to preface a little bit about the pprof stuff before I get into it. So what we're going to go over today is actually material out of the training that I do for a lot of corporations. So you're going to get a free peek at that today. I've been doing Go for over 5, maybe 6 years at this time. And in that time, I have maybe 2 or 3 times actually spent significant amount of time using pprof and torch graphs and stuff actually profiling the code. Now, you might wonder why that is. And part of it is because Go is one of those languages where you can just really get away with really bad code and it still performs really, really well. And so a lot of times, unless you're working on like some really serious enterprise software, things that have to scale very seriously, Go is just fast enough where you don't even care. Like, it doesn't matter. But when I did get into profiling, I found that it was really kind of daunting. And all the material I went to read about, like, I could not get a feel for, like, how does this actually work? And so it was really frustrating to me when I first got into it. So hopefully when we're done today, it won't be as daunting to you, because honestly, it's really easy to use. So let me go ahead and share my screen right here real quick. Get that started. All right, everybody should be able to see my screen. It's going to get bigger when I go into presentation mode, so don't worry about that. Let me just go ahead and I'm going to go ahead and copy the link here. If you're on the Go Study group on Slack, great. If not, I'm going to paste in this link into the chat on Zoom again. So basically what this does is this gets you access to the material we're going to go over today. You really don't care about anything in here other than the profiling. I did leave the chapter on benchmarking in here, and the only reason I did that is because some of the stuff we do in profiling today, we actually kind of use some of the benchmarks from the previous one. So if you're interested about benchmarks or just don't have that background knowledge, you can always go back and look at this. It's pretty easy to get through on its own. So we'll go into profiling here. I'm going to presentation mode here. Computer's slowing down here. Here we go. Okay. I'd like to be very interactive. So I'm going to try to keep an eye on chat. If I work on that, somebody's saying the link didn't work. Should literally be able to just click on that. Shouldn't do anything for it. Anyway, if you can, I'll try to get it done after we do the presentation too and try to get you hooked up. What was I saying here? Lost my train of thought. All right, it doesn't matter. All right, let's go ahead and just dig in here real quick. Oh yeah, I was saying I like to be very interactive. So I'm gonna keep my eye on chat, keep my eye on Slack. If anybody has any questions, either just jump in, raise your hand, type whatever, and I'll be here to help answer. And Jamie and Anchor, if for some reason I don't see it, please just interrupt me, because sometimes I get pretty involved.
We'll keep an eye on the chat and ask questions when they come up. The link, you have to log into your GitHub account, and that tends to work for people.
Yes, sorry, yeah. It'll require you to actually do an OAuth, and it's just a basic, simple OAuth for GitHub, so I'm not like getting any permission from you, so I'm not going to steal all your bases or anything like that. All right, so to start with, Go ships with a number of profiling tools. And so we're going to walk through a couple of things. We're going to walk through using pprof with the CPU profile. We're going to walk through using pprof with different memory profiles today. We're going to generate profiles from actual benchmarks, which is pretty handy. And for me, the one that I use the most is really generating profiles from live and running programs, because that's when I typically end up having to profile. So that's the one that I'll be looking for the most. And then how to generate torch graphs as well. And I'm just going to turn off my video on my end only because typically it will speed things up. All right, so everybody can still see my screen, right?
Yeah, we can see it.
Okay, perfect. All right. So that way, if you got low bandwidth, at least I'm not junking it up with video there. All right, so the best way to make your application faster is just by improving inefficient code, right? So it's pretty obvious, but as with anything, I think a lot of us struggle to find out, like, how do we know it's inefficient? Believe it or not, the pprof tool can do a pretty good job of sorting that out for you pretty quick. As we kind of hinted to earlier, there's different types of profiling. There's CPU profiling, memory profiling, and block profiling. So what are they? So CPU profiling is the most common type of profiling. It's the one that people go to all the time. And basically what it does is it interrupts the program every 10 milliseconds, and it records the stack trace of all the currently running Go routines. So while this can give you an idea of what's kind of a CPU bound, what it doesn't do, and it's really important to understand about your program here, is it doesn't take into account latency. So when we think about the way modern programs work, things are in wait states all the time, right? They're waiting on I/O, whether it's disk I/O, network I/O, any type of resources. So if you've got something that's blocking or just kind of in that wait state, it won't show up in the CPU profile, right? And I have seen people spend a lot of time on CPU profiles on their program and take things from, get 90% performance increases on these different parts of their program, and they put it out to production and see virtually no performance increase. And the reason why is because they made these things that were sucking up the CPU go faster, but that wasn't what was making their program slow. It was the latency. It was whether waiting on network or database or whatever it was. And so I always tell people, like, it's really important to understand that even though CPU is probably the easiest and most common type to go to, it can be very misleading. So we always want to keep it into account. And we'll kind of cover later on, we'll get into torch graphs, like how we know about latency and things like that. Memory profiling basically records allocations from the stack trace. By default, it's going to record 1 in every 1,000 allocations. This can be configured. Stack allocations are assumed to be free and they're not tracked, but it can be difficult to get a complete picture because it tracks allocations and not use. So again, just understand that last caveat. And then block profiling is basically looking for any time your program is blocking. And so we know it's blocked when you're sending and receiving on an unbuffered channel, sending to a full channel, receiving from an empty one, or if it's trying to obtain a lock on any type of mutex, okay? So that's when your program ends up locking. And this happens when it's waiting for resources too. Underneath the scenes, things will block and lock when you're waiting for system resources, network, all that kind of stuff. So that's kind of it. Block profiling is almost always the last profile you use. You want to make sure you've eliminated all your CPU and memory performance issues. I have literally never done a block profile. I've never gotten to the point where my program was not working efficient enough where I had to have blocking profiling. Now, you might end up doing block profiling in a situation where you just happen to know there's some problems with your code. So it's probably something was maybe not written properly, and you have a lot of contention for some reason. And that's when you use block profiling. So that kind of happens as kind of a result of, like, you just feel like, okay, I've done everything else. My program's not speeding up. Clearly, I've got some blocking contention in there. I need to find out where it is. And then this can be a good one to do. But literally, I've never gotten to that point, so I've been pretty lucky. It's not one that you want to try to figure out because blocking is a real pain to trace down. All right, so one profile at a time. Profiling is not free. It has a moderate but measurable impact on the program performance, especially if you increase the memory profile sample rates. So most tools aren't going to stop you from enabling multiple profiles at once. Obviously, you don't want to do that. If you run a CPU profile and a memory profile at the same time, it's going to skew both results, right? So we don't want to do that. So you always want to run one profile at a time, not more than one. So the rules of performance, I think these actually come from Dave Cheney, believe it or not, is never guess about performance. The measurements have to be relevant, meaning they have to be enough to actually meaningful enough to look at and go, yeah, this is a big enough measurement that I can actually tune it or make some type of, estimate about it. You want to really profile before you decide something is performance critical. Now, this one to me is the one that I can't stress enough. I can't tell you how many times I've caught developers doing pre-optimization. Is they'll write something and they feel like this is going to be the critical part of their program. They know that they just are convinced it's a mission critical area. And so they do all this time benchmarking and profiling, this one area of the code, and they've never even benchmarked the code as a whole, right? And it's really kind of frustrating because Go has a really good compiler and a really good optimizer. And so when you do this, yes, you're probably not, making it worse by trying to improve it, but you might be literally wasting your time. I've literally seen where already they'll do all this, and then they find out that's not the mission critical part of their code at all, by magnitudes. And in general, like if you're hitting a database or things like that, those are the ones that really kill you anyway, right? So in terms of relevance and magnitudes, it's always your resources that are typically your biggest blockers. So don't pre-optimize. That's kind of my little soapbox right there. And then number 4 is you want to test to know you're correct, right? So after you kind of done all your profiling, you're pretty sure this is what your problem are, do all of your optimizations and then measure again, right? So kind of just rinse and repeat. All right, so as a pprof 110 or later, you no longer need the binary used to create the profile to view the profile output. This is actually really cool. Now, why do we care about this? We care about this because when you work at companies where you ship a product and they're going to give you a profile, if they enable live profile, when they ship you the profile back to pprof, if they don't give you the binary, you can't view it, right? And that was a real problem. When I worked at Influx, this was a real problem. So we'd have people do profiles in production, and if they didn't ship us the binary, trying to recreate that binary was difficult. So this was a really big step forward. So this was really nice. So pretty sure everybody should be on 110 or above at this point, so you don't have to worry about it. In 1.9 or earlier, you had to always provide pprof with 2 arguments, right? You had to also give it the path to your binary. If you didn't do this, it wouldn't error out. It would just result in an empty pprof, all right? So if you are on 1.9 or earlier and keep getting an empty pprof, it might be because you didn't provide it the path to your binary. So just keep that in mind. Hopefully nobody has to worry about that. All right, so generating a profile from benchmarks is actually really, really easy. So if we want to run a pprof against a benchmark, we simply add a CPU profile. We just add this as a flag to the argument when we actually run the benchmark. So I wrote a benchmark in the previous chapter, which just literally benchmarks the string.split. And so if I go into this here, I'm going to copy this command. So if you're familiar with benchmarking, you know, really benchmarking is just go test, give it the bench and the split, right? So now you see we're actually adding this argument right here, which is CPU profile equals CPU.pprof. So let's go ahead and split my screen here a little bit. Let's move my screen over here. Let's get some of the stuff going here. All right, let's just get into the code. Actually, we're benchmarking the one from before, right? So I'm going to go into benchmarking. All right, and I've got my benchmark there, right? Where is that? Well, that's for someone. No, do I have this one here? Hold on a minute. Just look here. Where is this code? Oh, that is, I do have it here. It was in the right spot. Hold on 1 second. Oh, there's my benchmark. So if I cat split test, you can see that's my benchmark right there. It's my benchmark split. So if I want to go ahead and do the CPU pprof, I can go ahead and run this. That'll generate a pprof file. So it's going to run the benchmark. So it did that. And let's clear this out. And you see I have a CPU.pprof. I actually had one from before too. Should see that it's a new pprof at this point, right? So it actually generated a new one. So we're good there. Now notice it also generated the source.test as well. This is actually the binary. So basically what happens when you run a benchmark, it'll actually create a binary when it does that. And then it uses that pprof from the binary. So that's why you're getting that. So don't check that into your source code. You really don't need it. It's just junk when you're done. But just understand if you see that. If you're on Windows, you'll see, I think it's source.test.exe or something to that effect. So you'll see the binary on Windows as well. Okay, so at this point now we have that pprof, right? So now we actually want to run the pprof command and actually get into the interactive console. And so we can do that by simply from here just typing pprof. And we want to actually use the goto pprof, and you want to give it source.test and cpu.pprof if you're running 1.9 or earlier. I believe I can just do the pprof without this. And I'm used to using the new pprof too, which we'll talk about later. All right, so if I run that command right there, that gets me into the interactive pprof, right? So if I type help, it gives me all this handy dandy stuff right here. But fundamentally, there's two things we really tend to do. The most common thing we typically do is we run the top command. So you can see right there, I've got the top command. So if I issue top, that's going to get me this little table that comes back right here. So what that ends up doing is kind of gives me an idea of kind of my flat and my cumulative numbers, which is what I'm trying to look for, kind of big numbers there. Now, I've tried to do a good job of defining what flat and cumulative mean. And I've looked for even better definitions. If anybody ever runs across them, please let me know, because it just, I have not found a good definition for them yet, even out on the actual Go source code. Like they basically say, oh, this is, this is the flat and this is the cumulative. I'm like, well, that's what it says. It doesn't tell me what that is. But flat, from what I understand, refers to how much time was spent on that specific function or line of code. So if I were to look at, the strings.genSplit line right here, I would see that about 110 milliseconds was spent on that line of code. And then cumulative refers to how much time was spent up to that point of the line of code or that function, meaning that, so if there was a bunch of stuff happening prior to getting to this line of code, it would all add up to, roughly a second by the time we got to here, right? That's kind of what the cumulative means. So those are the different things. typically I'm looking at this number right here flat. And if I see big spikes in there, that gives me an idea like that's where CPU work is being spent. And that's typically where I'll tend to focus then and say, okay, that looks like, you know, if I look at top and I see the first time I'm looking.
Cory,
Yes.
sorry to interrupt. Can you just increase the font a bit because it might be difficult for a
Oh, yep.
see.
How is that? Is that better?
For command prompt, I'm not.
I don't know. Let's just get bigger like that. I guess about the same size like there. All right. If I make it too much bigger, I won't be able to see my screen either. I can always make it full screen like this too and do that. All right. So we'll do that.
Yeah.
That should be good. Okay.
Yeah,
So the one thing that you always have to look for, so the thing to remember is the benchmark we were running was in the strings package, right? We were just basically taking something out of the standard library, created a quick benchmark to benchmark. Now, typically you'd be benchmarking your own code in your own package. So we were looking for this strings right here, right? So we're looking for anything in the strings package because that's what we're testing. So you've got the runtime up here and you can all see kind of stuff happening there. So like this malloc CGC, right? This is the actually allocating memory at the runtime and stuff like that. We're probably not going to optimize that and really don't care about that. It's a sign that you've got garbage collection happening, right? But in general, we want to look for this strings package because that's what we're benchmarking. So that's what we're actually looking to work in. So at this point, it's like, okay, so I see that we've got this right here. What's really interesting though, is I ran a strings.split benchmark, right? And nowhere in here did I see the strings.split method show up. And it was interesting when I first did this, I'm like, okay, that's kind of odd. I would have thought from a top level standpoint, I would have seen strings.split show up first, but I didn't. Well, luckily we just look at the actual source code. And when you look at the source code for strings.split, and this is literally out of the standard library right here, you see that strings.split is literally a wrapper for strings.gensplit, right? So strings.split does nothing. There's no overhead there. And I bet it even gets optimized out underneath the scenes and literally just does a direct call to strings.gensplit at this point. And that's why when we look at this here, we're seeing the strings.gensplit show up and not the strings.split. So understand that that can happen as well with your own code, right? So you may be looking for a specific function to show up and say, wow, like I would have expected that to show up in my profile somewhere. And it's because of these types of things, right? When you're just directly making another call directly out of that call, you're just wrapping it. So that can happen, all right? So that kind of explains away that right there. So now to investigate further, we really want to do the list command. So what you can do is you can say list and then the name of the function that you're actually trying to list. So at this point, we say this, and I want to say, okay, well, now that I know that strings.gensplit is kind of where I'm spending my time, let's go ahead and list. You just type that right in like that. And let's see, did I type it wrong? Strings.gensplit. Feel like I typed it right. This could not find path. All right, why is it unhappy with me? Strings.go should be fine there. Oh, you know why? I don't know if I did that. That might be why. Huh. Okay. Didn't have my go past set. Really? Okay. Why are you going to do this to me here? It says it found it there. Turn my mods off. Make sure that's off. Of course, you know this never works in production, right? You're really not going to work. All right. So I can do one other thing. I shouldn't have to give it that. There's my top. What am I missing here? Oh, okay. I just upgraded Go yesterday too, so I don't know if I broke something. I didn't test this earlier. But what you're supposed to get is you're supposed to get this right here. And I really don't know why that I'm not getting that. That's literally the right command there. I've never had this happen before. Could try one other thing. So I clearly screwed up my path somewhere. I'm not sure how. I'll have to come back. I'm not going to waste your time on that. But that should work, okay? And if I find that it was actually something I set up, I'll actually post it later. But you should actually get this output at that point, which basically brings you into your code, right? So now what are you looking at here? What you're looking at this point is you're actually looking at the gen split function, right? This is the actual source code. And you can see as it comes line by line here, it's telling you that, it took 10 milliseconds on this line, 10 milliseconds on this line. This is your flat, right? It shows you that you've got flat and cumulative is how those columns line up. And then cumulative means that up until this point, it took 10 milliseconds in the code, and which obviously makes sense because right here. And then it got to here, 200 milliseconds has elapsed, and then got to here, and 620 milliseconds has elapsed. So what's really cool about this now is this is basically you looking at your actual code line by line and seeing where the time is being taken in your actual code. So this is really, really powerful when you're trying to optimize and look at performance, because it takes all the guesswork out, right? You can literally look and say, oh, like right here, 620 milliseconds was taken into account. Now, we can look at this and make an educated guess that we're making a make statement. So what's happening? We've got memory allocation going on. Now, maybe if this was like one of our functions and we were in a loop or something like this and we saw this happening, we might decide to pull this make out of the loop and recycle that slice at that point to avoid memory allocation every time, right? Like there's different things we could do. But the number one thing you're trying to do is, first of all, you're trying to see like where's all the time being taken. Now, we used a benchmark from a system library, right? We used the split method from the system library. This code's already really highly optimized, so it's not like I'm expecting to come in here and go, oh, look here, I can really optimize this code. This is more showing how quickly it is just to use pprof, to use a top command and a list command, and bang, you're right in here looking exactly in your code where any time is being taken up actually in your code, right? So it's pretty simple. And so I think this is really daunting to people originally, but fundamentally this is pretty quick to do. So I'm just curious if anybody has time, literally copy this benchmark right here. Just put this benchmark on your local machine and run it and see if pprof's working for you. I'm really surprised that my list isn't working. I've never had that happen in all the years I've done this. But again, I literally just upgraded Go yesterday, so who knows what I broke.
That's okay. I have a quick question since you're on the screen right there. Yeah. What does it look like whenever you have a loop? Does it just show you each time through the loop, or the cumulative total every time through the loop?
So what it typically will show you is like, so that's where the flat and the cumulative really matter. It's not always a guarantee, because part of it is that it's taking a time slice, right? So when you're in that loop, if it's like got conditional logic to maybe be in or not in that loop, it may or may not show you how much time was spent cumulatively. And it also means how long did you run the benchmark, I believe. So like if you ran the benchmark a lot, it'll just keep adding this time all the time in there. That's something that, to be clear, I'm not 100% certain on. This is part of where I keep coming back to the Go team and like, can we just get better documentation on this stuff, right? Like I really feel we need better documentation. I don't get too worried about it because, as you'll see once I get going in here, I don't actually use the pprof tool like this very often. I find this to be interesting, and I consider this what I call microsurgery, right? So by the time I end up in this area where I'm running an actual list command, I'm in microsurgery land. I've already identified with a different tool, which is the torch graph we're going to look at later, which is where my big block is, like where my big amount of, heartache kind of is in my code, like where all my blocking is going or all my performance is being eaten up. And I use that to kind of isolate from there. And then I'll drill into this at this point to find out like line for line. So this is the last thing I usually do, but it's the first thing you usually start with because that's what people are expecting to see. So I probably didn't answer your question. Hope again, like I say, if you look for documentation out there on pprof, it's very, very sparse, unfortunately.
Yeah, that was helpful. Thank you.
Okay. All right. So that's kind of that piece right there. You can also see this in a visual format by listening to web commands. So I'm curious to see if this is going to work or not. So that works, which is shocking, right? So if that works, my list command should work. So this is actually an SVG. Let me zoom up in here. Take it down a little bit. That it will generate right from there. So you see all I did was type web, and it actually shows me. So I'm coming in from my testing, and then it shows me, my bench split, which is what I ran, and then strings.split, which is immediately a wrapper for strings.gensplit. Now, if I zoom out a little bit, notice how the colored stuff right here, this is my code. Anything that's red or a different color than just black and white, that means it's mine. Anything that is a different color is either the system library or the system runtime. So it's kind of neat, like in a bigger profile, you can very quickly isolate like what's my code, like what can I control versus what is code that is out of my control, but maybe still eating up time. This kind of shows you the branching, right? So if I look into strings.gensplit and I come into this, let's say I wanted to optimize this. I would look at this one right here and see where it says runtime.makeslice. I know that that's doing allocation. Now, the only way I can optimize that allocation is if I literally just remove it, right? Or make it so I reuse an allocation somewhere. So I probably can't do that. The strings.count is taking very little time, but the strings.index is taking a little bit of time, right? So at that point, I can say, okay, out of this slice right here, 17% is being spent in my strings.index. Maybe I look at optimizing that or making, try to make it so I don't make that call, that type of stuff. In general, I don't find this view super helpful. Effectively, you're just looking for the big box. If you find the big box, that's where your time is being taken, right? That's kind of the deal. But again, we're benchmarking a system function here, system method. So I'm not expecting to find like big things to profile. If this was your own code, you'd be able to like look at it and go, oh, like I see over here in this one spot, I'm doing a bunch of maybe unneeded work, or it's taking longer than I expected. And it kind of helps. I'm a visual person, but I really don't get much out of this one. And I'll kind of show you why once we get past it. So you can do that. It may or may not help. Sometimes it's really helpful. Sometimes it's not. Here's the thing about profiling. One of two things happen when you profile. Either A, you immediately see the problem, or you don't. Right? It's really that black and white. It's never like, oh, if I spend a little bit of time, I'll find it here really quickly. It's either it's obvious or it's not. And so when it's obvious, it's great. And when it's not, it's painful to try to find and dig up. So, all right. If the web dependency doesn't work for you, it's because you need GraphViz installed. So I've got a link here in there. Basically, just go to GraphViz and download the piece that you need. Whether you're on Linux, Mac, or Windows, they have all the things. So if web didn't work, you kind of got this error like, hey, do you have it installed? It's just stating that. So if you run this locally, you're going to need to have GraphViz. Okay, so now let's talk about running a memory profile. So basically, it's the same thing we want to do before. So we want to run our benchmark, but this time we actually want to run the memory profile. Okay, so before we had the CPU profile, and this time we want to do a memory profile, and there's a couple different things we'll get out of here. So let's go ahead and just run that real quick. Get over here. All right, run that memory profile. And if I look, we'll see that it did, in fact, update the memory profile. So I have that available to me now. And then all I have to do is run this. Hopefully, this will work this time. All right. So now I'm in there. I'm in the pprof again. And same thing we can do like we did before. We can just list the top, okay? So if I list the top, I kind of get the same thing, but now it's by memory, right? Now, obviously, we know from looking at the other profile that there's a memory allocation happening in there. The only one that's happening is in strings.gensplit. And of course, now let's hope this works. Come on, work. Really? Okay, so this is why I always put all of the examples in my actual slides. You're supposed to get this. So it's really frustrating that it's not working, but I'll figure it out. We're going to get this back at this point, right? So if I list top, we get the strings.gensplit. And then I can literally just do the same thing again, which is just the list strings.gensplit, issue this command right here. And that again drops me right into my code. So you get the same thing here, flat and cumulative. This time it's in terms of memory, not in terms of like % of time taken up. So we can see right here, this is the only spot we're actually doing memory allocations, which we would expect, right? So again, there's not much we can optimize out of this. This lines up directly with the CPU profile we just did. So it's like, oh, okay, the CPU profile and the memory profile, they all kind of agree as to where some of this time is being taken, so on and so forth, right? Again, nothing for us to optimize here unless we were in a loop and wanted to recycle this, that type of stuff. Then we could maybe not allocate every loop, things like that. But in general, this is just telling us, hey, here's line by line where it's happening. Again, this is what I consider the microsurgery. This is one I've already isolated like where my big performance problems are from my torch graph. Then I would come into these functions at these lower levels and do these, listings like this. So again, pretty straightforward for the memory profile. And this is allocations, okay? So the other one is in-use objects. So it's the same thing. We can use the same actual pprof that was generated before. But this time I give it the in-use objects command when I launch pprof, and so it'll give me a different one, okay? So if I do this here, if I exit this, so notice before I had the alloc objects, right? That's what I used before. This time I'm gonna give it the in-use objects to get into there. And if I issue the top, we don't see anything, right? Now, the reason we don't see anything in use on this one is because the benchmark's really, really small, so we have no measurable objects, okay? So this is one of those things where sometimes you might actually get an empty pprof. If you're doing benchmarks, you'll get that. If you're live profiling a program, you'll never get that. So don't worry about that. But we'll come back to the in-use objects when we see a bigger profile here if we get time today. All right, we actually have an exercise that we typically do in class. I know we don't have time for that today, but if you want to do that on your own time, this is really kind of a neat exercise to do and run through this. And then I actually have the solution for you as well, right? So you can actually see like this is how you'd actually run the benchmark, and this is what the benchmark actually looks like. And then you can actually do all the actual profiling commands that list here and kind of take a look around. So if you're looking to run your own benchmark and see how that works from a profiling standpoint, you can do that on your own time. And of course, if you ever have any questions on this stuff, don't hesitate to get a hold of me in the Slack channel as well. I'm always available for that kind of stuff. Okay. For me, though, that's kind of the benchmarking, some of those micro programs, stuff like that. I spend most of my time benchmarking live programs. Okay, that's really where I spend most of my time because I care about the performance as a whole and how things are working out there, and you get a bigger picture. So you can actually use the NetHTTP pprof package to enable live profiling of your actual program. So this is actually pretty cool. Now, this might be the first time you're going to see somebody import an actual package and put an underscore in front of it. This is what they call importing for side effect. And the reason we do this in the pprof package, if we actually open this up here, we will see, let's just get into the actual code here somewhere. Just want to get to the actual code. Where's the init in here? You'll see that they have an init block in here. This is probably pretty small. Let's make this bigger. And see what they're doing here? So if you already have an HTTP handler or an HTTP service in your program, if you don't, you can wire one up. But if you do, they're literally just wiring in these endpoints for you. That's all they're doing. And so this allows you then to, at this point, take a live profile of your actual program. You don't need to understand that for what we're going to do here, but just understand that works. And what's really neat then, let's go ahead and run this locally here. Let's get rid of this. We'll come back to that one in a minute. Let's see, where are we here? Okay. This is my web server with the main.go that's actually got the net pprof in it. And see it's listing on host 8080. If I actually go to these debug pprof endpoints right now, you'll see that this is actually the actual endpoint to dump all that stuff. So there's really nothing going on because it's just a website with under no load right now. So if I hit this endpoint, you're not going to see anything. But I can actually, from this point, dump the entire stack trace, right? So what does this tell you? This tells you that if you're running this in production, you're going to want to secure these endpoints down. You don't want the public getting at this, right? You only want this for invisibility if you launch this in production and secure these endpoints down. So while you can do it in production, and many people do, just understand you got some security cleanup to do out there. That being said, that I talked about there's a negligible overhead to running pprof and taking live profiles in production. And I have already seen where a lot of times the performance is only being degraded like under heavy load in production, and you can't simulate that. So at some of the places I've worked, we've had companies literally leave the pprof endpoints up, and when they started having load issues, they would grab a live snapshot while they were in production and send it to us, which was fantastic. And it was a little bit of a hit, but not enough of a hit where it took their service down. And so it made sense, right? So I'm not giving you permission to run this in production. You have to make that decision on your own. But just know that if you did, you would not be alone. Like, this is not an uncommon thing for people to do, but it does come with some risks. So just understand, like, it might really degrade your performance, things like that. Okay, with all that being said, the web server that I brought up really is pretty simple. It's just for a demo app. And all it has really is just kind of this one endpoint, this handler here. And its entire job is just to tell you whether or not it looks like an email or not. Now we can see my super fancy regex here for email, right? Pretty simple. Obviously, you won't really validate emails because no regex can. But it's just to simulate some type of load here, right? So this is my app. This is what I've got up. And this is what we're going to profile right now. So if I go ahead and do this, I can use the go-to pprof. I can give it how many seconds I want it to profile for. And then I can give it this endpoint, right? So I give it my pprof profile endpoint. And so if I run this right here, let's see here. You can just run that. And you will see that will actually go out and profile in 10 seconds. Seems like eternity when you're training a class. But it's going to sit there and take a measurement over 10 seconds, and then it saved this actual pprof, right? And then it drops me right into the interactive pprof, like I'm there already, right? So this literally took a live snapshot of that running program. And so what's the most common thing I do? I issue top, right? I want to see what's going on. So I go ahead and do that. And now look at this. I have an empty pprof, right? So you're already asking yourself, I did everything I'm supposed to do. I enabled my endpoints with the pprof. I've got my program running. It's definitely there. I did this profile. I issued top, and what happened? Well, it's actually really, really obvious when you think about it. Our program's not under load, right? We're not doing anything. It's just a web service that's up and running, and it's waiting for something to happen. So because nothing's actually happening, there's nothing to measure. So understand that it doesn't do you any good to take a profile of something that's not under load. There is a really cool tool out there called Go Work. And basically all you have to do is say go get work. And then what that does is I can basically create load on my actual service at that point, right? So if I want to do this and take an actual measurement of this, let me open up yet another window. And let me get out of here. And so this is kind of one of those things you have to have both hands right at the same time. So I'm going to go ahead and put load on it. And then I'm going to take my profile. So now you can see on the left-hand side that thing's getting hit pretty hard over there as that go work command hits. So this time when I take a profile, I should actually get some results at this point. Okay, so I got my profile. I can cancel this now. Is it out of here? All right. So now if I issue my top command, voila, right? I've actually got something I'm looking at. So this is actually pretty cool. Now notice in here, I don't even see my stuff show up at all. Like it's so far down the line. And this is where I always tell people, right? Like when you optimize, like you pre-optimize, your stuff might not even show up on the radar. However, we still want to see this, right? So the easiest way, if I really want to see what's going on here, we can use this web command real quick, right? So I hit web, and I bring up my pprof, and now I get something a little bit different. Now notice I've got, if I zoom out here a little bit, see how I've got two different actual threads going on here? Why do I have that? Because I'm using a web service, and a web service uses Go routines to run their handlers. So you see actually two different stacks here that are running, which is kind of neat. So you've got this stack down here, which is my main, my listen and serve, and all that kind of stuff. But over here, we have got, where is my actual handlers for doing everything? I'm looking for my main. Here's my main handler right here, right? I've got that. And then I can see that out of all of this stuff that's going on in a standard handler, 60 milliseconds is down my pipe, right? Everything else is read and write requests and stuff that the system is doing, so I don't have much control over that. So out of all the stuff that's happening over here, I don't make up probably only half of my actual handler. And if I come all the way down here, it doesn't even split and show. Finally, I see this log.printf in my main. Here's what's really interesting about this when I looked at this the first time. If you looked at the program, I was logging this out, right? I was just logging out this my basic web service, logging things out. Notice how that takes almost 5 times as much effort to print that out to the screen than doing the actual work of actually validating the email in my program. Isn't that hilarious? So when you look at that, you're like, oh, like if I want to speed this program up, you know how I do this? I take out the log. I just stop printf. Like that's it. It's gone. And I can speed this handler up by a factor of 5, just like that. So, it's shocking sometimes when you actually realize where your actual time is being taken up in your program. It can be very unexpected. And then down here, if I actually look at my main is email, I can see basically the amount of work that's happening at this point is I've got the is email, I've got the match string, I've got the do match, and I've got the do execute. So probably not much I can do there. I might show you later on with the flame chart, might be a little easier to understand. Actually, there is a place to optimize there. You just don't see it here because of the way this is looped out. Okay, so this is the way I kind of got into that and looked at that profile there. So this is a live profile. As you can see, a lot more moving parts. But again, it highlights everything in red so you kind of know where to look for your stuff. All right, so we just did that. All right, that being said, there's a brand new pprof tool that's out there, which is actually quite a bit nicer than what ships with Go. I still don't know why it's not shipping with Go. I have no answers for you. It was supposed to ship with Go 1.10 and never did. And then so when I went out to try to find all the new stuff, I had to literally ask somebody on the Go team and go, where is this? And they're like, oh, it never shipped. I'm like, but your release note says it did. And they're like, yeah, I know it does. So it's really confusing. So there's a misconception that there's a brand new pprof that shipped with Go, but it actually isn't. And you have to actually go and get that. So if you just do the go get right here, this will get you the new pprof. All the commands work the same way the other ones do, but instead of saying go tool pprof, you just say pprof. That's it. You've got a new binary in your path at that point, in your go path bin directory. That's where that puts that. So now you can just run pprof that, which is actually quite a bit nicer. Okay. So here's the neat thing about this now. I can actually run the pprof here at this point. I want to tell it to get a running profile again like I did before, but this time I'm going to tell it to run its own actual web service, and I'll show you why we want to do that. So let's go ahead and get this up here real quick. Let's go ahead and exit this. Let's see, I suppose I need my go work command again, don't I? So that's going to be that one right there. Let's see, so I want that one right there. Oops, that would be why. All right, so I'm going to take my pprof as I'm hitting the endpoint really hard there. Wait my 10 seconds to grab all my data. All right, so notice this actually launched a web UI for me, right? Now, why did it launch a web UI for me with this pprof? Because I told it to. I said, I want you to launch your actual web UI for me. And what's nice about that is it drops me into this right away. So you can see that this is the same type of result I got from this one, but it's laid out differently, right? So they're using a different algorithm in here. What's really cool about this, though, is I know from my code, if I go back to here real quick, find my code, I've got a handler here, and I've got an isEmail function, right? So sometimes it's really hard when you look at these to find out like where your stuff is. If I just type isEmail, right, it highlights everything I'm looking for. So now I go, oh, okay, there's my isEmail function right there. So if I want to find something really quick, it's really easy. If I'm looking for like, you know, where is all my stuff from main? I can do that, and it kind of gives me my entry point. So this search up here is super handy, especially if you're looking at a really, really big pprof. And then all you have to do is zoom into it, right? So that's kind of neat to go like that. You have different views over here at this point. So if I want to see my top from here, I can do that. So I can spit out my top. And this one gives me quite a bit more at this point, so I can go down and take a look at it. Now, it's not an interactive pprof, right? Like I can't list a command. But here's what this gets me. This is the best part. This gets me my flame graph. And technically, this is an icicle graph. It's upside down. Somebody at Google decided one day they didn't want to do flame graphs anymore. They want to do icicle graphs. So they did this. I have no idea why. It makes no sense to me what they did. So now this is typically where I want to see where my main is at this point. So I can highlight that, right? So I see my main. This is where I know I want to actually optimize my code. So all of this other stuff really is noise to me. It's all the runtime. It's the web service, like the listeners and all that kind of stuff, which I know I can't optimize that, so I don't care. I really care about this right there. Look at that, right? I can click on that. And now I'm looking at just where my time is being taken in this actual torch graph. Now, before I get into this, let me explain a little bit about torch graphs right here. Kind of give you a little idea here. All right, so basically flame graphs and torch graphs, now these are upside down, I haven't updated my slides yet, is the x-axis just shows the stack population, and it's sorted alphabetically, it's not by the passage of time. And the y-axis shows the stack depth, all right? So basically, you just see everything, and the wider things are, kind of so to speak, so the wider they are, that's how you know how much time things are taking. So the top edge just shows the stack of like, this is the actual end of this stack, the last thing that got called, and you got your kind of stack depth. This is your complete width all the way across here, and they're proportional. The colors don't mean anything, by the way, okay? So top down or bottom up, in our case for an icicle graph, shows just your ancestry of your stack depth and your calls. And then the widths are proportional, right? So E looks like it's about a quarter of what F is. D, you know, makes up E and F and all that kind of stuff, right? So that's how that breaks down there. So if I come back to my torch graph now, right, or my icicle graph, we can see that in my main handler, my isEmail is taking up a little bit of time right here. I've got an actual lock that's doing something which I can't help. But then obviously the majority of my time right here, if I look at this and I can see 40 milliseconds is being taken up here, or 10.81% of this, versus over here in my main email, this is 2.7% of my program, right, or 10 milliseconds. So this is where I can quickly say, okay, well, maybe I just want to get rid of this printf. That's pretty cool. But what about my main isEmail, right? Is there anything I can maybe optimize in this? I don't know. Let's take a look at this. I've got the match string, the do match, the do execute. So really there's nothing I can do here. They actually made an optimization, I forget when it was, maybe in 110 or 111, where it's actually optimizing out. If we look at my code back here, this used to be something I could optimize, but now the code does it itself. This is the really cool thing about Go. Their compiler gets better and better. I had this must compile in here. See the regex must compile? Notice that you don't see a must compile in here. Do you know what they actually did? Their optimizer actually pulled this out so that when I run the isEmail, it only runs the match string now, because the only thing that changed in the program is this variable right here, this didn't. And in prior versions of Go, like if I switch back to 1.9, you'll actually see that this must compile shows up in my actual stack depth here. And that's actually where it takes a lot of time. And one of the optimizations I would do is I would take this out here and I would just make it a constant out here in my program so I didn't have to do the must compile on a regex that never changes. They've since gotten so good at optimization, they were able to detect that this didn't need to run every single time I called is email. So they optimized that completely out of my code for me and made my code faster. That's completely wild when you think about that. So there's actually nothing for me to actually optimize in here anymore because they took that out of there, which is pretty wild. In fact,
I think if you had made that not a constant, it would have had to evaluate it each time. Email regex.
Yes. Yep. You're right. But it's interesting that this is a relatively new optimization for them. Like this is within the last couple releases.
Yeah, that's a common mistake is compiling each time in the loop.
Yep, exactly. Which is why I did it, right? And now they've gotten so good, I can't even show people my crappy code. It's like, no, like I did this bad on purpose. And it's like, it's unbelievable. So yeah, it's interesting how good they're getting. So then you can, if you want to reset the view, you can just do, let's see, where's my reset?
Cory, this looks like a little unbelievable. Can we look at the code that produced this flame graph? Because this really looks unbelievable to me.
Yeah, so if we look at the code, this is the code. Like this is literally the entire set of code. I mean, if I expand this out, you can see, you know, my package main or whatever, but this is literally the code that produced that flame graph when I did the profile.
This is amazing, man. Amazing.
Yeah, this is great for you.
And it's really unfortunate that I think a lot of people are really scared of this because they feel like so daunted by the concept. But I've done a lot of profiling with really big programs. Like, I mean, I've had things that were like, you know, social graph programs, and I would put endpoints under load, and then I would run my live profile. And I'm telling you, like in 30 days, I took some of these endpoints, I literally optimized the latency and everything out of them by 97%. Like that's how good I got them. And it was literally by coming into here and going like, okay, so, you know, if I've got my code that I'm looking for, here it is right here. And now you've just got your stack. You basically look for the fattest stack, right? The widest one, and you work your way through that one first. And you make that one skinny, then you make the next one skinny, and you make the next one skinny. And pretty soon it's just a bunch of really big spikes. And what you're really looking for is you're looking for, if I have it here, I don't even know. You're looking for a lot of skinny spikes like this, right? You don't want, you know, you got some big ones down here, but if they're the system, that's fine. But as long as you've got all these really skinny stacks, that's great. But as soon as you've got a bunch of really wide stacks, that's where you know that your time's being taken up. And that's a great indicator that you should optimize that. So these are my go-tos. Like I go to flame graphs immediately when I live profile programs because I'm a very visual person and it helps. I know a lot of people go right into the interactive pprof and they must be like mad scientists because I don't know how they're able to figure it out. They're clearly much smarter than I am. I just use the flame graph. But you can see how literally, if I know this one command, right? If I know this one command and I know how to put the pprof endpoint in my code, which is literally just this, right? And I've already got a handler going. That's it. That's my magic. I can now live profile any of my running programs.
Wow, that's amazing. We're right up on time. So if there's any questions for Cory, I don't think I see any in the chat. Nope. Well, thanks again, Cory. That was amazing. Is there anything else you want to add?
I mean, there's an exercise at the end that you're happy to do on your own as well. But for the most part, you've got all this material forever now. So if you got any questions, let me know. I'll circle back and find out why my list commands aren't working and post them either in chat or you know in the Go study group. Really not sure what happened there, but again, like I say, I probably broke my Go environment yesterday.
Yeah, not a problem. Yeah, thank you so much. That was amazing.
Yeah.
All right. Well,
Okay.
if there's no other questions, we'll go ahead and end it here. And thanks again, Cory.
Hey, thanks for having me. I really enjoyed it.
Yeah, it's definitely my pleasure. Let's try to do this again.
Absolutely.
All right. Well, that concludes today's Go Study Group. Thank you, everybody, for joining.
Thank you.
All right.